Hello everyone, and happy either Saturday, Sunday, or Monday. Before we jump into the new types of equilibrium, I'm actually now in OneNote so I can write. We are going to learn one more type of equilibrium before spring break, and that is called KSP, and that is solubility equilibrium. Before we do that, though, this is the second slide, so this is the introduction slide or the head slide. We are going to review something that we did in, I think it was September, okay, which was precipitation reactions. And I actually did not leave you enough room, so I suggest you go get a separate sheet of paper to do this work on, because I did not leave you enough room at all to do this work. So again, we're going to review a little bit and then talk about KSP, because once again, I lied to you a little bit in the beginning of the year. So it says, write the overall and the net ionic equation for the reaction with zinc nitrate with sodium hydroxide. So here we have to remember how to write formulas. So zinc, which has a charge of +2, and nitrate, which has a charge of -1. This is the formula here. And then sodium hydroxide is this Na-1, and this is OH-1, so the formula here is NaOH. This is a double replacement reaction. So we get zinc OH. Now why we need the 2 here, or this 2 here, is that zinc has a +2 charge and OH has a -1 charge. And then we get NaOH, each with both, NO3, each would have a -1 charge. So that's okay. We don't need to do any crisscrossing or anything like that. And again, these are all aqueous, which means they're dissolved in solution. And now we need to remember our, way back ago, our solubility rules. All nitrates are soluble, so they get AQ. So then this one must be the precipitate. So then it asks us to write so we did the overall molecular equation. Now we have to write the net ionic. And this is from a long time ago. I'm going to write the net ionic in green. So remember, to write the net ionic, things that are AQ, you dissociate. So this dissociates into zinc +2, plus, remember this comes up in the front, 2 NaO3-, plus, oh, and I forgot to balance. I always forget to balance. So we need a 2 here, and a 2 here for balancing. Sorry about that. And then for this one, this is also AQ. This guy's also AQ. So it's 2 Na plus 2 OH-. The solid gets brought down. And then this dissociates into its ions. And I'm running out of space, so let me move over a little bit. There we go. So 2 Na+, and then 2 NO3-. So again, the rules are that aqueous get brought down and broken and dissociated into their ions, and the solid stays together. Now, if you remember, what we do is we cross off the things that are the same, or the ions that are the same. So if we look, there's NAs, they cancel, and there's hydroxides, and they cancel. So we're left with zinc +2 plus 2 OH-, produces zinc hydroxide in the solid form, or the precipitate form. So now what does this look like in a reaction? Well, let's say you had a beaker, right? Here's your beaker. At the bottom there would be some precipitate, and the precipitate is zinc hydroxide. It would settle down to the bottom. And then you would have the things that are crossed out. Those are spectator ions, so they would be floating around in the solution. Now here's the question. Are there any excess ions that weren't able to precipitate because there's a limiting reactant? So to do that, and let me change my color so it looks colorful. So to do that, let's write my favorite color to write in this one is purple for some reason. I don't know why. So to do that, we have to calculate the moles. So we'll calculate the moles of NaNO3 first. So if we scroll back up, we see that the liters are 0.1. The moles over liters for molarity. So the liters are 0.1, and the molarity is 0.3. So we're solving for moles on top. We cross multiply, and we get moles equals 0.03. And then we will do the same thing for sodium hydroxide. Again, we want this 0.1 still the solution. If we go back up, we see that the solution is still 0.1 milliliters. But this time the molarity is 0.4. Moles are on top, so we get that moles are equal to 0.04. Now we have to determine which one is limiting. Now you may say, oh, this one's less, or this one here is less, so it's limiting. But that's not the case, because remember, you have to divide by the coefficient. If you end up, no, I'm not going to do it, because it's obvious, but if you end up dividing this one by its coefficient up here, it ends up being less than 0.03. It's actually 0.02. So we know that NaOH is limiting. And this one is in excess. So what that means is that there will be some zinc ions still floating around in the solution because it's in excess, but there will be no hydroxides because it's limited. Alright, so let's look what else they asked us to do. So which ions remain in solution after the precipitation? Well, we found out those. It's going to be sodium, NO3, and zinc plus, because this is in excess, so not all of it can combine with, or there's not enough hydroxides to combine with all of it. And we're going to order them from least to highest. So from least to highest. So we know the least easily. Okay, the least by far is the one in the limiting reactant that's in the precipitate. And that's, so the one in the limiting reactant that's in the precipitate, and that's OH, so that's the least. And we know in some order, in the highest, and we're not exactly sure what order, we have to figure that out. In the highest, there's going to be some zinc plus in solution, some NO3 in solution, and there's going to be some zinc plus in the solution, zinc plus 2. We now need to figure out how much, because that's what it asked the second billet, it's the third billet, but we're first going to calculate the mass of precipitate on the bottom. So to do that, we need to start with the moles of the limiting reactant. So we know we have 0.04 moles of NaOH over 1. And the equation tells us, if we scroll back up, that for every 2 moles of the limiting reactant, or NaOH, we have 1 mole of the solid product. So for every 2 of NaOH, we get 1 mole of the solid product. So now we're at moles, and I did this for you quickly ahead of time. We know, and then you multiply by the molar mass of the solid product. And the molar mass of the solid product, which I calculated ahead of time. I thought I did. Hold on, let me it did, is 99.396. And when you multiply across the top and divide by 2, you get 1.99 grams of the solid product, which is zinc hydroxide. So if we scroll back up, the next thing we have to do is calculate the molarity of each of the ions remaining in the solution. And we know that there are 3 ions remaining in solution. There's Na+. Okay, what else is there? Let's go back up and look. There's NO3-, and there's some amount of zinc plus 2 that was in excess. Okay, so it's very easy to find out how much of the spectator ions are. So there's 0.3 moles when we calculated the original molarity, there was 0.3 moles of this guy. So there was 0.3 moles of, we'll start with sodium hydroxide. So there was 0.03 moles of zinc hydroxide. Not hydroxide, I keep on doing that. Zinc nitrate over 1. And we know that for every 1 mole of zinc hydroxide, nitrate, sorry, zinc nitrate, I don't know why I keep on doing that. There are 2 moles of nitrate. Because of the 2 here. So this ends up being 0.06 moles of nitrate, which we have to then, that's the moles of nitrate, and it wants the molarity, so we have to divide by the volume. Now remember, the volume is additive, because you're pouring them together, okay? So the final volume is 0.2 liters, which if you do this math, you get 0.30 m. Remember, why is it additive? Let's go over why it's additive again, because you're pouring these two things together in a cup. So when 100 plus 100, so 100 plus 100 is 200 milliliters, so the volume has increased. So that's the amount of one of the spectator ions, which is nitrate. What's the other spectator ion? The other spectator ion is sodium. And we were told in the beginning that we know from up here that there are 0.04 moles of sodium hydroxide. So there are 0.04 moles of sodium hydroxide. And this one is easier. And we know that for every 1 mole of sodium hydroxide, there's only 1 mole of Na. So this you could have avoided if you realized this. So there are 0.04 moles of the sodium ion. And we divide this by 0.2 because it's still in the same cup. And if we do the division, hopefully you can do this in your head. We get 0.20 m of Na plus. So this is of Na plus. And this one down here, let's just finalize our answers, was of NO3 minus 1. And then we have one more to do. And this one is always the hardest. So this is, remember, this is in the precipitate. This one is in the precipitate. But it is in excess. So not all of it combined. So not all of this zinc was able to combine with the hydroxide. So we have to first figure out how much of the excess NO2 is left. And whenever we do this, we always start with the moles of the limiting reactant. So we know that there were 0.04 moles of NaOH that reacted completely. Okay? Per the equation, right? If we look at our equation, it is a 2-to-1 relationship, right? So for every 2 moles of NaOH, there's 1 mole of zinc nitrate. Again, where am I getting this from? I'm getting this from the original equation, and I'm finding how much of the zinc ions reacted. Okay? So if I do this, I find, and I do this math, right, I find out that there's 0.02 moles of zinc NO3 reacted. That's how much reacted. Okay? So how do I find how much is left? Well, I know how much I started with, because I calculated that already. I started with 0.03. So I do the subtraction. So there's 0.03 minus 0.02. And there are 0.01 moles of NO3 that did not react. So now I specifically want to know the amount of NO2. So you'll notice that for every 1 mole of zinc nitrate, there's also only 1 mole of this guy, right? There's only 1 mole of zinc. So it's a 1-to-1 relationship. For every 1 mole of zinc nitrate, there's 1 mole of zinc because there's no number here. So there's also 0.01 moles of zinc ion, and we divide that by the liters, which is 0.2. And we get 0.05 moles, or molarity. So if we were going to order from least to greatest, the least amount is NaOH. And then if we look at our calculations that we did, so this is the most least, then would be zinc, right? Because some of it precipitated into the precipitate, but there was excess of it, so some of it is left in the solution. Then if we look at our math, next would be sodium plus, and then the highest, which we can delete these now, the highest would be nitrate. So this is a blast from the past, and so when we start doing our review sessions, we're going to go over these reactions. But in some ways I was lying to you. Some of that precipitate, let me go back, hold on. Some of that precipitate that we put at the bottom actually does dissolve a tiny, tiny, tiny bit in water. And that's what I'm going to talk about in the next video. So I lied to you.